Okay, it's running. Good. Thanks so much for Sandra. Hi, Pablo. Okay, let's get started. So the first announcement on logistics, as just in case you might have missed it, I announced on e-courses that I now decided to make a midterm exam, a week-long take-home exam. And I had some interaction with some of you, and it looks like this is the best solution. And that avoids a conflict with a particular day of some other midterms. And then that was also make my life a little easier, because it's hard for me to come up with a problem set that can be solved in just a couple of hours. So I hope that will be the best solution. And so I post the problem set on March 4th, just like what I always do for the homework problem. And you all gone for a week and submitted the week later by the end of Friday. So it's sort of like a doubly big homework, and the difference though is that you have to do it by yourself. And I distribute a pledge form you are supposed to sign and submit, and so that you do everything by yourself. You don't get any help from human beings, internet. If you get some help from your dog, I can't prohibit that, but anyway, so that's the idea. And you can consult lecture notes, lecture videos, lecture slides, as well as textbook and homework solutions, which I'm sure would help. But that's the idea. So hopefully that avoids various concerns some of you had. Go ahead.
Does not help from human beings include Piazza questions regarding lectures or something?
Question from
Like
lecture?
during the exam, can we ask questions on Piazza about lecture material?
Oh, Piazza. I think Piazza, you can use Piazza, but to the extent of clarification of the problems,
Okay.
rather than tips on solving the problem.
Yeah, but what about lecture material questions? That can we ask questions?
Oh yeah, sure, that's totally fine.
Okay.
Is any questions? Is everything clear? So I think that's the best solution. I hope you agree with that. Okay? All right, so let me then jump into the lecture, okay? So I guess that some of you are getting a little lost in the math, so let me try to recap what's going on here, and also try to translate what we have discussed with this weird classical wave equation to probably more familiar language for many of you using operators, and hopefully that would actually sort of tie up the knots so that everything starts to make sense. So anyways, that's the idea. So here's the recap. So what we have done in the beginning of the QFT class is to rewrite quantum mechanics you're familiar with, but you may have a large number of particles. And we also put in the chemical potential and interactions. The repulsive interaction among particles. So this is actually a system of many bosons. Many bosons with repulsive interaction. Short range. And if you have this kind of many-body system, normally you don't know how to solve the system. And the main thing I want to convey is that it turns out, if you switch from quantum mechanical language to QFT language, it turns out that you can solve this problem within some validity condition. And that solution turns out to be described by a classical wave. That's the part that is the least the most counterintuitive, I'm sure. But that's the thing I've been talking about, yes.
So we know that it's about bosons instead of fermions from the Hamiltonian only because...
Yeah, from the Hamiltonian, you wouldn't know. So in quantum mechanics, writing Hamiltonian is not good enough. Then you have to, in addition, declare that this is a system of identical bosons.
Okay, okay.
In a QFT, you don't need to do this, because once you have a single field that does describe system of identical bosons from the onset, so you don't need to impose additional condition on top of it.
Okay.
Thanks for the question. Yes?
How do we deal with the system of fermions then? In QFT?
Yeah, we will talk about fermions, hopefully today, later today. Any other questions? Okay, so what we talked about is that this system is identical to QFT given by this Lagrangian, which I have written already many, many times by now. In a way, we verified that these two theories are totally identical to each other by writing down the many-body wave function using the QFT language that reproduced the Schrödinger equation in quantum mechanics language. So we know they're the same thing. But using this language, within some validity condition, it turns out that this is actually semi-classical. Namely, that solving classical field equation turns out to be the same thing as solving highly quantum state of matter. And you have seen that cool video that when you go to low temperature with a bunch of identical bosons, and you're looking at this de Broglie wavelength in a homework problem, when you go to low temperature, each particle starts having very low momentum. Low momentum means each particle has a stretched out wave function. Because de Broglie wavelength is given by h bar of the momentum, and we know expectation value of momentum squared in a thermal bath goes like temperature, so this really keeps going down as you go to nanokelvin temperature. And again, you're checking in a homework problem why nanokelvin is the right temperature scale for this kind of Bose-Einstein condensate to form, so you get some intuition on the numbers that way. And once this happens, then what you're talking about is this weird state of matter where you have a bunch of identical bosons sort of overlapping on top of each other. And that's a highly quantum mechanical state of matter if you use the particle language. But the amazing thing about this particle wave duality is that this highly quantum state of matter, if you insist on using particle language, turns out to be a very simple problem of solving classical field equation if we switch to the field theory language. So that was a sort of surprising thing. But I hope you see two things at once here, namely that one thing is that QFT allows you to solve problems you cannot in quantum mechanics, which is already a big improvement, because now you can handle systems you couldn't do before. And second, you see this manifestation of particle wave duality. So we often start with particles because that's where we have some intuitions on what particles are, but you have already learned in quantum mechanics class that that is actually not the right description, because particle behaves like a wave. There's nothing which is purely particle, but there's always, partially particle, partially wave. It's always the same thing. And it turns out that you can switch it around, then start with a wave description of matter. And if you quantize a wave, which we have done with this Lagrangian before, you can get particles out because the wave is actually an operator which acts as plays the role of annihilation creation operators. But instead of talking about quantum field, if you go back to classical field, you can describe this highly quantum state of matter instead. So the role of classical and quantum is switched between particle and wave. So normally, we start with the classical particle, and if you quantize it, you get wave. But what we are doing here is that if you start with a classical wave, if you quantize it, you get particles out. Because this wave or field operator is the radiation creation operator. But what we discussed in the case of the coherent set of a harmonic oscillator is that even though you are dealing with quantum mechanical harmonic oscillator, you can define a state which behaves as if it were a classical pendulum. And I have shown you this movie of how wave function really moves back and forth. In the same way, if you start with a wave, and if you quantize it, you get particles. But if you form a coherent state of these particles, then it starts to behave like a classical wave. And description using classical wave has distinct advantage over the language of particles, because I have shown you, you can find a solution of static Bose-Einstein condensate. You can find a solution of moving Bose-Einstein condensate. You are checking that in homework problem now. And there's another solution. If you have sort of the potential well that looks like donut shape, you see a fluid going around. Then you find something is quantized in this, and you're working that out. So the velocity given by this circulation is quantized in unit of integer times something, where something is actually a combination of fundamental constants. So that gives you a particular stability of the system. So it turns out that you can describe sort of macroscopic motion of the system much better using the language of classical field, which is very difficult to discuss if you insist on using the standard quantum mechanical language of particles. Yes, I see a hand up there.
Just to make sure, the process of quantizing involves changing functions to operators.
Huh?
That's because operators have discrete eigenvalues instead of continuous function values.
Oh, that's right, that's right. Yeah.
Right, that's why it is,
Mhm,
okay.
mhm. Any other questions? So this is sort of the recap of what we've been talking about. Yes?
From the homework, I didn't quite understand how that question talks about like circulation.
So,
Yeah, how does that, what does that mean?
you mean this mathematical expression?
Yeah.
Ah. I thought you have seen something like this in electromagnetism, where, let's see, what is the, if you have an electric current, then you find that there's a magnetic field going around it. And Ampere's law says this integral of the electric field is proportional to the electric current inside this loop. So it's the same expression. And this is meant to be dx dx plus dy dy. Or you can also write this as b along this the azimuthal direction integrated over the azimuth. It's the same thing. So in this case, d theta is understood as b bx plus y dy. And just a shorthand notation of this line integral is given by the symbol that you have this integral symbol, but you go around the loop. So that's what this expression means. Does that make sense?
Yeah.
Okay, so that's just a definition of what a line integral means. Okay, so then what I'd like to do now is that we sort of completed the story using classical wave as a useful description. But I would think that you're probably more familiar with dealing with the quantum system with operators. I'd like to sort of do a little translation on how the same thing can be discussed using operators. And hopefully that would sort of make this whole thing better. And it turns out using operators is, they don't commute after all. So it's a little tedious and a little technical, but at least you can see the language of operators, which I hope will help you understand what's going on. So that's what I would like to do now. And whenever I give research seminars on the research I do, and when I find the occasion that I'm coming back to some language which I have abandoned just a little while before, I always use the language that revenge of operators. And my students always laugh because I'm a Star Wars fan and so on. But anyway, so revenge of operators now. So what does it mean? First of all, it's useful to talk about momentum space. And we have done this over and over again, also in your homework problem, that you can define a state by creating a particle. So this is a creation operator, right? And take the linear combination of that state with a particle in position x using some weight. And this capital psi turned out to have the meaning of the wave function. So we talked about this over and over again. And a very simple wave function is the momentum eigenstate. And it's not worry about normalization for now. So what that means is that this combination can be understood as an operator that creates a particle of a definite momentum. So what you see is that psi x, which is the field operator, and psi dagger x has the meaning of creation operator at a position x. But its Fourier transform is actually an operator that creates a particle of definite momentum. And depending on how you normalize the state, the most sort of a rigorous thing to do is to put the system in a periodic box. Then you can correctly define the normalization of the state and write it in the following way. So it's just that you are expanding the field operator now in a Fourier series. I hope you have seen that somewhere. And P has to take the values given by 3 integers on XYZ direction, where momentum is now quantized in the unit of 2 by h bar over L, so that if you put that into the exponent over here, it satisfies the periodic boundary condition. Right? If you go L in x direction, you pick up the phase of I 2 by h bar over L nx L over h bar. So the whole thing becomes 2 pi nx. And exponential of I 2 by integer is 1. So it satisfies the periodic boundary condition. Then you can fully define these individual momentum modes. And each of these modes you can check that they also satisfy the standard creation annihilation operators, the commutation relational creation annihilation operators. That they don't commute and give you one when you're referring to the same momentum, but they commute completely if you're referring to different momentum modes. So the field operator can now be regarded as just a collection of a bunch of creation annihilation operators for individual momenta. And the reason why this is a little bit more intuitive is because whenever you act this on the vacuum state, that gives you momentum eigenstate. And because we have done this before, when you have Hamiltonian on a state created by the field operator, it turns out it's the same thing as acting Hamiltonian for point particles on this coefficient function capital psi. In our case, that is this derivative operator acting on that one, where this turns into P over H bar. So you find that this is indeed an eigenstate of the Hamiltonian with the usual kinetic energy of P squared over 2n. Yes?
So in defining the psi variable over there,
So capital or small psi?
the capital psi, I mean, I'm talking about the state.
This?
No, the state itself.
This.
Yeah, so I understand that the creation operator acting on that will create an a particle of momentum P. But what does the integral do? Does that create a particle of momentum P everywhere in space? What is the role
That's
of the
right.
integral?
It's really everywhere in space.
So you have one particle at each position?
You create one particle in position x,
Okay.
but you smear it for the entire space, weighted by this exponential.
Oh, I
And that's
see.
the idea of momentum eigenstate, right? If you had a momentum
I
eigenstate,
see.
P is definite, so delta P is 0, then uncertainty principle tells you delta X is infinite.
I see.
So your particles spread out of the entire space from that galaxy over there to the other galaxy over there, in principle. That's not realistic, but anyway, so that's the idea.
So the narrowness of the width of the particle that's being created will depend on some arbitrary function that is the normalization factor?
Yeah, so this function can of course be a wave packet,
Yeah, sure.
which may not be spread out for the entire
Got it.
space. So in that case, your delta X is finite,
Got it.
but then the momentum is also a little uncertain.
Mhm.
And I hope you have seen this kind of wave packet in quantum mechanics
Yeah.
class too. So it's still the same idea. So after all, we are dealing with a quantum system. And I've been telling you that the QFT and quantum mechanics are equivalent. It's just that QFT is more powerful. So what you're seeing here is that instead of talking about this field operator in position space, you can basically talk about the field operator in the momentum space. And momentum space field operator is really creation annihilation operator of particles with a definite momentum.
Got it. So why do we couple creation and annihilation sometimes? If you're just creating particles, why don't we just stick to either creating it or destroying them? Why do we like combine them sometimes? Like sometimes we say psi dagger, psi dagger, psi dagger. Like why are we combining them instead of just sticking to one?
I'm not
Like
sure
for example,
that's
psi dagger psi is the same as not creating any particle, right?
That's right, but this is the way you count the number of particles, right? So that's a number operator. A dagger A in harmonic oscillator tells you n of the excited state n. So in the case of the creation annihilation operator of particles, A dagger A is the number of particles. So you're not changing the number of particles because you annihilate one and create one. You don't change the number, but instead you find the eigenvalue, which is the total number of particles you have in the system. Okay?
Yeah.
Yes?
So can we also say A dagger A in momentum space also giving us the
Yes.
number?
So it's the same way that number operated in position space This is the number density. If you integrate the space, that's the number operator. But if you plug in this mode expansion into psi, and just work out this integral, you find that this is sum of all modes and number operator for each momentum. So it's the same idea. We're just switching from position space to momentum space, but everything else is the same. But the advantage of momentum space is that when you create a particle in momentum space, that's already an eigenstate of the free Hamiltonian. And of course, we eventually would like to come back to this interacting bosons, but at least at the level of the single particle, then it probably makes it more intuitive, I hope. And that's why I'm talking about this. I hope that helps. And I saw Jackie.
No, it's okay.
The same question, okay. Any other questions? All right, so having learned this idea of using momentum modes to write the field operator, we come back to this question of the Hamiltonian that has interaction. And what you can do is to just plug in this mode expansion into psi, perform the x integral, and get a Hamiltonian in momentum space instead. And the free part of the Hamiltonian then looks very simple. So this is the first term, which basically tells you that you count the number of particles in momentum p, because it's a number operator. And each one of them has the kinetic energy p squared over 2m. So at least it makes a good sense what's going on with this Hamiltonian. So this is really a collection of point particles. And when a point particle has momentum p, it gives you the kinetic energy of p squared 2m. And if you have two of them, it's twice as much. If you have three of them, it's 3 times. And then sum over all possible momentum modes in the system. So if you have this P1, P2, P3, you just sum P1 squared over 2m, P2 squared over 2m, P3 squared over 2m. And if you have two particles with the same momentum P1, then you have twice P1 squared over 2m. And that's what this Hamiltonian is telling you. So far, very simple. Now, if you look at this, the chemical potential term, I already told you that psi log of psi is the number density. If you integrate it over space, that's the total number of particles, which can be also written in the same way in momentum space. So now you find this. But already at this stage, you notice something is going on. When the kinetic energy is bigger than the chemical potential, I can put them together into a single parenthesis. This is positive. Then, not putting a particle in momentum with P is the ground state. And if you put more and more particles into that momentum mode, that gives you higher and higher energies. So the vacuum state is the ground state. So that's what we're familiar with. But when momentum is smaller than chemical potential, then what happens? If we have no particles, that's a vacuum state, it's still 0, because the number operator is 0. But if you put one particle in that momentum, you lower the energy. If you put two particles into that momentum mode, you lower the energy even more. So having positive chemical potential means this system has no ground state. because you can keep occupying low momentum modes to keep lowering energy indefinitely. So that's a bottomless pit. There's no bottom to it. So positive chemical potential really does something weird. And that's what we talked about when I think you asked the question about the statistical mechanics, that if you look at the Bose-Einstein distribution function, this probability as a momentum, function of momentum, when p squared over 2m is mu, it blows up, then becomes negative, which is totally ridiculous because it's subopposite probability, so something is going wrong. So that's a stat mech language. This is the quantum ground state language. And the same thing in field theory language is that potential we talked about for the field, ignoring the interaction term, is minus mu psi star psi. And if you plot this on a complex plane of psi, real part, imaginary part of some psi, it looks like this, because it goes down quadratically. Then the field psi can keep rolling down the hill, and again, that's the bottomless pit. You can just keep going down indefinitely, and there's no ground state. So you see the same thing in 3 different languages now. This is the quantum operator language, this is the stat mech language, and then there's the field theory language. And the reason field theory is powerful is that instead of writing down operators, you can just draw a picture and you see it. So it turns out that field theory, once you get used to it, which takes time, but once you do, makes it actually more intuitive and visual, because you can draw the potential and you can tell that there's no ground state. But what we have done is to put this interaction in, and on the field theory side, what that does for you is to turn the potential around, because once field becomes large enough, quadratic term will eventually dominate over the quadratic term because of higher power. Because lambda is positive, it turns around and creates a ground state. And that's what we looked at. So once again, you can draw a picture to find that now you can find a stable ground state. Using stat mech language, this is difficult, because how do you include interaction in this kind of the distribution function is not clear. And you can do it to some extent, but I don't attempt it here. And I even don't know how I can solve the system if I try it that way. But quantum operator language still allows us to do something about this. And that's where I hope things become a little bit more clear, because certainly you have seen operators before, and that I hope would give you a better understanding of what's going on. I see a hand up, just go ahead.
Yes, sir. How did you get from del psi to there? I was just confused. So when you combine del with psi, which are both operators, there in the definition of the Hamiltonian.
Okay.
Yeah. So you said del psi dagger, for example. Yeah, there. So you're combining 2 operators, right? So what does it mean to take the del of an operator?
So psi is now expanded. It's gone. And I think these effects are like that. And when you take the root of them, and you have to remember that X is no longer an operator, it is now devoted to parameter. So what the derivative does is to just transfer X over here. So that's what derivative does on the field operator. And when you take this one and their permission conjugate and integrate over x, then that will give you delta function. So AP for the annihilation operator and A dagger Q for the creation operator need to have the same momentum. And that's how things turn into A dagger A with the same momentum modes. And because the derivative pulls out P over HR twice, you get P squared over 2M. So that's how you can work this thing out.
So, but psi was originally the annihilation operator, and the other side that we created was a state, right? So how is that operator the same as that side?
Let's say, so psi is an annihilation operator, and A is also an annihilation operator.
Yes.
So neither of them is a state.
Okay.
And both of them act on, let's say, if we have the creation operator instead, you can act it on the vacuum state. This is the point particle at position x. When you do it on the other side, you create a particle of the momentum p spread out in the entire space. But when you sum up over all these momentum modes, then you can create this momentum, that momentum, this momentum, this momentum, so on and so forth, to create a peak somewhere as a delta function. And that's nothing but the position eigenstate. Again, this is the same idea as in quantum mechanics. Is that okay?
Yeah, that makes sense.
Any other questions? Yes.
So.
What's your name, by the way?
Oh, Sarah.
I'm sorry?
Sarah.
Sarah.
With this Hamiltonian, we were talking about like infinitely smaller energy if we were just looking at the without the interaction.
Uh-huh.
So is it possible to have such a system if we did
Yeah,
it
so,
like
right, so that's basically the Bogoliubov I briefly mentioned, I think, on Wednesday. So if you turn this repulsive force off, and you can even turn it the attractive one, then what used to be the stable Bose-Einstein condensate all of a sudden crunches and collapses to a point because it's unstable now. The particles are not attracting with each other. They would like to come close to each other. And coming to the point means the density is blowing up to infinity. And infinite density is the same thing as having large psi, because psi log of psi is the number density. So this picture of particles collapsing a point is literally the same thing as the field turning on and running down to infinity, because that corresponds to the infinite number density. So you do see this in experiment by something called Feshbach resonance. So you have the system of a bunch of atoms. Then if you have, let's say, some electric field or something, when you diode the electric field, you can change the nature of interactions among atoms from repulsive to attractive. And once you cross the threshold, it goes and then it bounces back, boom, and that's the Bose-Nova. And I put the link in my slides to a movie of the Bose-Nova. It doesn't look that great like in Hollywood movies. It doesn't have sound, for example. So without sound effect, it may not look impressive, but you do see something is really exploding. You first implode, and then it explodes, and that's a Bose-Nova. So this really does happen, namely instability in going to infinite density. Thanks for asking. Any other questions?
But we can't explain that from this Hamiltonian, because
Yeah, yeah.
it seems like we can infinitely go down.
Right,
So if we
right,
turn to
right. If lambda is negative.
Right. So there's no way to tell that phenomena from this, like this equation. You would know that the density is going to be going up, but
Right.
we wouldn't know that would definitely cause Bose-Nova.
So the explosion part is not something you can understand by this, because it explodes only because when the atoms come really, really close to each other, they would once again repel. Otherwise, they can't sort of explode. And that's not put into this Hamiltonian. So the only thing you can tell from the Hamiltonian alone is that it goes whoosh. And this expansion part requires yet more term in Hamiltonian to represent even stronger repulsive force when they come really, really close to each other. Okay, that's a good question to ask. Yes?
In our Hamiltonian, we see that there is no ground state if the chemical potential is actually bigger than the kinetic energy, right? What happens if they're exactly the same? So like if you have like a bunch of particles with exactly the same, like the kinetic energy which is exactly equal to the chemical potential.
Then you can, so that's something called zero mode, and that's also an interesting discussion on its own. Then you have a particular momentum where you can keep adding particles to it without changing energies.
Okay.
And that kind of thing also happens in some systems, and that's an interesting thing on its own. But right now, to have a well-defined system, you have to put in this repulsive potential anyway, and once you do so, there's no zero mode anymore because it always costs you some energy. And then, so it turns out that you don't have to worry about it, at least for this one.
Okay, okay. So you're either like no ground state, one ground state, or which is the vacuum state, or infinite number of ground states.
That's right. So in our case,
Okay.
we have this infinite number of ground states
Okay,
at the
okay,
bottom
okay.
of this potential.
Thank you.
Okay? So to understand this better using operator language,
Oh, sorry, I have a question.
okay, go ahead.
Is the mu chemical potential constant or?
That's the constant, yeah.
It's a constant.
Yeah,
At
so
which-
right now I have this idealized situation where everything is spread out in infinite space, everything is constant in space, so chemical potential is also constant in space.
No matter how, no matter where we are at the, on that graph, the chemical potential still stays the same.
That's right, right.
Okay.
So that's the idea. So it can in principle depend on space, but right now I'm taking that a constant.
Okay.
So in order to include interaction, then the Hamiltonian is still safe for this two-body part. Then comes the interaction part. Oops. Where did I write it? Oh, right here. P, Q, P prime, Q prime, P minus Q. And this function V of P minus Q, if you actually start out with the potential over here, it is just a Fourier transform. And you can work this out once again just by substituting in all the expansion of P into this expression and perform the x integral. That gives you this chronic delta for the momentum conservation and these creation annihilation operators. So tube size on the right will provide two annihilation operators here. Tube side diagonals on the left provide you these two creation operators. Potential is now Fourier transform. In our case, potential delta function is actually constant. In our case. And this delta function comes from integral of x of exponential star, exponential star, exponential, exponential. Only when exponents add up to 0, this integral doesn't oscillate and give you a finite answer. And that's how you get this Kronecker delta. And once you actually look at this, the interpretation of this terminal operator is very simple. You find two particles coming in with momentum q and q prime. You annihilate each one of them, then create two particles with momentum p and p prime due to this operator in the middle. So this term in the Hamiltonian describes scattering process of two particles coming in, two particles going out, like, and the pool, billiard ball hitting each other and clink. And then this really does represent the momentum conservation, that initial state momentum q plus q prime and the final state momentum p plus p prime have to be the same. So this is the free part of Hamiltonian, where you don't have interactions. And this interaction term in the Hamiltonian really describes the scattering process among the atoms hitting each other. Yes?
So is Vx in the integral over there equal to lambda over to psi dagger?
So in this case, this is actually lambda delta function x minus y, psi dagger x, psi dagger y, psi y, psi x, integrated over delta x, delta y. And when you prove the integral of y, you can substitute y everywhere by x, and that's how you get this one. And I did mention that if we have a long-range potential between particles, this is the potential between two particles. And in our case, this potential between particles is a delta function. That's why I wrote this form from the beginning. But in general, you can have more general interactions between particles given by long-range potential.
What about the mu term?
Mu term just became this one, right? So mu is
Oh, I see,
constant.
it's okay over there.
Right. So I have first term that has derivatives, mu, so the second term with chemical potential. In the last term, for the potential we took is delta function, so it's just constant, times 2 annihilation and 2 creation. And 2 annihilation, 2 creation represents this interaction that two particles come in, they go click and go to two final state particles with momentum conservation automatically imposed. So that, I hope, would make this Hamiltonian look more intuitive. You have three particles with this chemical potential you have to deal with, and it has interaction in it. Then you ask the question, okay, now that we have a Hamiltonian, what is the ground state? Now we resort to this operator language to find out what the ground state is. And for that purpose, we first focus on the zero mode. Then Hamiltonian is minus mu A dagger A, and I probably should have write A of 0 for the zero momentum, but there's a shorthand notation. I'm just writing A in A dagger for the zero momentum host. And then I have this, and factor volume I have to be careful about. I didn't write it. So I can work this out on the fly. Shoot. So I put that in here. Three. So if I focus on the zero momentum mode, this is the Hamiltonian. Then I said, you can build a coherent state using this creation operator for the zero momentum particle. evaluate the expectation value of Hamiltonian, the elevation operator acting on the right just pulls out eigenvalue F. Creation operator acting on the left pulls out eigenvalue F star. F is a number, so it's just a complete conjugate. And same here. And this is the same form as the potential for the field we looked at before. And you find that minimum where F star F is mu over lambda L cube square root. And this is supposed to be the ground state with a zero momentum. So that's why I have been telling you that talking about the semi-classical approximation is the same thing as the coherent state. Now you can see you can really build the coherent state for the particle with zero momentum, which means that particle with zero momentum now has an expectation value. And then you say this is a condensate. Particle is somehow stuck in the ground state. And that's sort of the rough meaning of the word condensate. And mathematical definition is that the annihilation operator has an expectation value. And that's something we have seen in the case of harmonic oscillator. You have this P and Q motion along the circle, and when annihilation operator has an eigenvalue, annihilation operator is basically x plus IP, so you have specified both x and p, more or less, with the minimum uncertainty. And then annihilation operator is an eigenstate, therefore it has also expectation value. So that's the thing we looked at in the case of harmonic oscillator. Now we are doing the same thing for particles. So your ground state is now linear superposition of different number of particles. So n is now uncertain, spread out in this direction. But that allows you to have certainty in the phase direction. And when delta theta is finite with more or less well-defined phase, then you can talk about interference of two Bose-Einstein condensates, each coming with their own phases, but when they overlap, then you have the behavior of the wave that depends on the difference between the phases. And that's the fringe pattern I have shown you the data of, I think last week. So this is the representation of manifestation of number of phase uncertainty principle we talked about in the case of the harmonic oscillator. But now that using the harmonic oscillator to describe particles, this uncertainty is not in the uncertainty in the energy levels, but uncertainty in the number of particles. And theta is the phase of the field operator psi of x we talked about. And because psi of x has the well-defined phase, and that's why we can deal with the classical wave equation. And you can let them overlap with each other, interfere with each other, and then how you get this fringe pattern, not as a probability wave, but on one-shot measurement, you see the fringes. And that's really interference pattern among two classical, more or less classical waves, not matter wave. It's really a macroscopic wave. So that's what we talked about, and now you see this in the operator language. And hopefully knowing two ways of describing the same thing gives you a better idea of what's going on. Any questions? Yes?
So The reason why we are looking at the zero momentum system is because we basically want the temperature to be very, very low, almost zero.
Well, that's an excellent question. I also have to look at the non-zero momentum modes too, and that I haven't done yet.
Okay.
So that's the next thing I will do.
Okay.
Thank you for asking. Any other questions? Yes.
Is this basically like Bose-Einstein condensation?
This is the Bose-Einstein condensation. Yes. Any other questions? Yes.
Why would you say that that F state is a F the expectation value of A is
So F,
constant state?
F is the eigenstate of the relation operator with the eigenvalue F. So that's why A acting on F just gives you number F.
Yes, but why is it called?
Or is it called condensate? So the idea is that when this number is non-zero, you get a sense that, especially when this is large, again, X is P harmonic oscillator language, this is very large. And you have a tiny blob because of minimum uncertainty state. So compared to the number, you have tiny uncertainty. So that means you can say number is fairly well defined. Delta n is much smaller than n. And you have done that in homework problem because delta n turns out to be square root n, which is much less than n when n is large. And at the same time, you also have the phase rather certain now, because when delta n is square root n, delta theta is 1 over square root n from the uncertainty principle. So both number and phase are relatively well defined, and having this number means that this is basically the square root of n, because f star f is the number operator. So you have large number of particles stuck in the ground state, and that's the meaning of the word condensate.
Yes, thank you.
Does that make sense?
Yes.
It's just a word, but at least it can convey some intuition behind it. Thank you for the question. Anything else? Okay, then non-zero momentum moves. So what do you do? Starting with the Hamiltonian up there. In our case, the V is the delta function, so you can go ahead and do this integral, and this actually turns into a constant. Is that right? Yeah, that's right. And then you try to diagnose this Hamiltonian now for the non-zero momenta, but now you realize that this is a complicated problem. But in the same spirit as taking the semi-classical limit, we can do something called the mean field approximation. Which means that out of 4 creation-addition operators, I substitute the condensate we talked about for 2 of them, then replace them by numbers as their expectation values, and then your Hamiltonian now looks quadratic in A, namely A dagger A. That's something you know how to deal with, as long as you can ignore interaction compared to the expectation value. So because A in A dagger now has expectation values, it can still create one-eyed particles. But what we are saying is that the most important things they do is to give you an expectation value, and creating more particles or annihilating more particles is higher order interaction. So let's ignore that for the moment. So out of 4 factors of creation annihilation operators, you replace 2 of them by their expectation values or their condensates. Then you find Hamiltonian that is quadratic in A and A dagger. Then you know what to do with it. So that's the approximation, mean field approximation, which turns out to be the same thing as a semi-classical approximation we have done using the classical field language. And when you do so, 2 of them are now 0. Then this P and Q are the same. So now you find the Lagrangian, Hamiltonian, which is something you know how to deal with. This is just a number. This is also a number. And you have AP, dagger AP, and summing of P. So this is just extra correction to the kinetic energy you had before. So that's easy to deal with. Except that there are other ways of putting the condensates into this. Instead of turning one annihilation operator to condensate and one creation operator to condensate, that gives us this kind of familiar looking term in Hamiltonian. You can also take 2 annihilation operators replaced by their condensates and keep 2 creation operators instead. Then you find a term that looks like this. These 2 are 0 replaced by condensates, so P plus P prime must be 0. That means this P prime is negative P, so you find a term like this one. And that looks kind of odd. You may not have seen this before. And you can do the same similar thing by replacing 2 of the creation operators by their condensates. P and P prime are now 0. Here's 0, which means Q plus Q prime must vanish. Then you find a term that looks like AQ, A minus Q. Now you are looking at some strange looking Hamiltonian. And here I haven't really done the complete algebra by working out all of the coefficients, but if you do, at the end of the day, the Hamiltonian turns into this form. Plus pieces that are cubic in creation annihilation operators and beyond, which corresponds to interactions among the particles, and we are ignoring them. And we are keeping the pieces that pick up these condensates while dropping the interactions. Yes, Jackie?
There may be a lambda.
So it turns out that when you actually pick up these condensates, size of the condensate is determined by minimizing this one. So F star F is mu over lambda L cubed. And if you put in these expectation values into 2 of the A's, I get mu over lambda, that cancels lambda, so it turns out that everything becomes order mu. and lambda sort of disappears from the expression. And thank you for the question. That's a good question to ask. Yes?
Is the tool coming from the fact that you can choose two combinations of A dagger and A?
Yeah, so this is actually a little tricky because you have to move
Yeah.
this out. And then there's also some cancellation going on between this term and that term. You have to work everything out more carefully, and then you arrive at this expression at the end of the day. And I'm not really showing that algebra because it just takes sometimes, so I dropped it. Thank you for the question too. Yes? Oh,
No,
oh, you
sorry,
just
just
go.
checking, yeah.
Okay. Any other questions? And so now this Hamiltonian looks weird. Not just A dagger A, but you got also A dagger piece. But it turns out that as long as the Hamiltonian is quadratic in A and A dagger, you can solve it exactly. And this is the part a little technical, that's why I didn't do the operator discussion first. But just so that you know, this is something you can do.
I have a question.
Yes?
So, simply by looking at the Hamiltonian we have, and we can abstract the meaning of it with knowing that there is single particle interaction, basically A jag A, and then we also included the process of adding opposite momentum particles, which means that can mean momentum conservation. I don't know if it's implied. And the other one is another case for which you take away the particle with the opposite momentum.
That's right. So the last term basically means you are taking particle with momentum P and particle with momentum P, and then it just disappears. Because you are annihilating both of them. But the total momentum is still conserved because you're removing P and minus P together.
Then do we not neglect pair interactions? Like from the beginning?
Yeah, so we are definitely ignoring this because that would involve 4 powers of the creationization operators.
Yeah.
So we regard that to be higher order.
Yeah. Okay.
Okay, does that answer the question? Yes.
Could you repeat again why we're working in momentum space and not, for example, energy space or position space?
This is strictly momentum space.
Yes, but why?
Why? Because that's the simplest. That's
Oh.
just the pragmatic reason.
Okay.
Any other questions? Yes.
The last two terms of the Hamiltonian, it looks like we're creating two particles and meanwhile annihilating two particles. Should these two events happen at the same time?
They can happen at the same time. So you can, for example, draw a diagram like this one. You have particles P and minus P coming in, and then disappear. Disappear in this case means that become the part of the condensate. Or you can all of a sudden create particle with P and minus P.
Can these two processes performing separately?
Right, and this is I would sort of in some sense quantum fluctuation going on. Your ground state is constantly doing 2 particles disappearing, 2 particles appearing. So as a result, your ground state will be a linear superposition of vacuum and 1 particle with momentum P, 1 particle with momentum minus P, 2, 2, 3, 3. So that's what you would expect. So if the Hamiltonian can turn 2 particles into nothing, or nothing into 2 particles, then these states are constantly turning into each other. And to diagonalize the Hamiltonian, your eigenstate would be this infinite series. And that's the part a little complicated. And if you want to know more about these details, there's bows.pdf on B courses lecture notes. And I'm actually expanding it to talk more about this hopefully ready early next week. And so that's something you have to do. And the way you do it is by using something called Bogoliubov transform. You guys see hand up or yes? Go ahead.
Yeah. So why shouldn't P and minus P be anti-parallel vectors? How do they actually combine? They should be going in opposite directions. I'm kind of confused, like how are two particles with opposite momentum?
Well, sort of particle P coming in this way, another one coming from the other way.
Oh, it's that way, okay.
They meet in the middle and disappear,
I see, okay.
or the other way around.
Got it.
So, what you're supposed to do in this case is, very roughly speaking, you have a Hamiltonian that looks like this. And then you try to complete the square. And obviously there's some coefficients going on here. So I put in the coefficient cosh and sinh. Then it turns out that this is cosh and sinh. And the reason why you can do this is that if you define a new annihilation operator, which is a linear combination of creation annihilation operator, then its conjugate you can show is that they satisfy the usual commutation relation between creation relation operator. And you can sort of see this by your eyes, right? Here, I put in this one. What doesn't commute with A is A dagger, it's cosh. So I get cosh squared. If I look at this piece here, that's sinh. What doesn't commute here is this piece here, like if you sinh squared. But in this case, you get A dagger A, that's -1. So you get cosh squared minus sinh squared, that's 1. So that's how you can recover the usual commutation relation operation. So what you get in the end is that your Hamiltonian can be cast into the form of just B dagger B, and B dagger satisfy the usual commutation relation. And then you know what the ground state is, namely that your ground state has to be annihilated by this now transformed annihilation operator. And this linear combination is what we call Bogoliubov transformation. So what we are looking at, if you use operator language, is fairly complicated. For the zero momentum mode, you have the coherent state. And for non-zero momentum, you bring in pair of particles with the opposite momenta and build the state which is the Bogoliubov transform state. And you build this for every momentum. And this is the linear combination of states with different number of particles, 0, 1, 2, 3, and so on. This is now a linear combination of states with 0, 1 pair, that's 2 particles, 2 pairs, that's 4 particles, 6, 8, 10, and so on. And you form that weird linear combination for 0 momentum modes or the non-zero momentum modes. You take tensor product of all of them, and that turns out to be the ground state of entire ABC. It's more complicated. That's why I told you at the beginning, before launching into the discussion on Wednesday, that if you choose the path for trying to use classical field or operators you may be more familiar with, it turns out that classical field is way easier because you just can go ahead and write down the solution for it. But just to understand what's going on, the ground state described by classical field can also be understood using operators and states. It just looks more complicated, but you see macroscopic number of particles occupying the 0 momentum states. So you have sort of a big peak of number of particles in momentum space at 0. And here you have also occupied certain number of particles for the non-zero mode that looks kind of like this. And around the point where p squared over 2n is about mu, you have the transition of occupying the state with a lot of particles to the states more or less not occupied at all. And this transition happens in this form, that if you actually go ahead and solve this, this is also in the slides I'm going to post later on, is k plus mu square root k plus 2 mu, and k is meant to be just the kinetic energy of the momentum mode. So what you see here is that when momentum is very large, I can ignore mu. K square root is k, becomes 1. Cosh being 1 means that eta is 0. And if eta is 0, the Bogoliubov transformation is trivial. A and B are the same, A dagger and B dagger are the same. So you haven't done any transformation, which means you haven't really occupied the state. On the other hand, when k is small, you're looking at this small momentum region, then I can ignore k, then this mu is partially cancelled by square root of mu, square root of k remains, so I find the whole thing is square root of mu over k. So when k is small, mu over k is large, so area becomes very large, and when area is very large, what's going on here is that both cosh and sinh are exponentially large, and more or less the same. So B operator is basically A plus A dagger. B dagger is A dagger plus A. That's the case where you are occupying a lot of particles into the system because you really have to look into this linear superposition of 0, 2, 4, 6, and so on to find the ground state. So that sort of confirms the original intuition you had that when this is negative, the original free Hamiltonian is unbounded from below, you start to occupy that momentum with a lot of particles to minimize the energy until the point that interaction will stop it. So that's the intuition that you are occupying low momentum modes with many, many particles because of that term, and that's indeed the solution you find after going through all these steps. So as you can see, it's a little complicated. That's why I didn't do it initially, and I did try to do it with the classical field instead. But you can do it with the operators. You can see more details in lecture notes. And hopefully, comparing these two pictures, that confirms the intuition in the language you may be more familiar with. I hope that helps. Yes, Kate?
I have a question. Understanding that the ground state of the Bose-Einstein constant state is a tensor product.
Uh-huh.
I don't translate that tensor product, because if I understand initially, I understand coherent state,
Uh-huh.
and I understand ground state,
Uh-huh.
but when it combines together, I just don't get this.
Yeah, so what's going on here is that when you expand this out, and for the zero momentum mode, I have this linear combination of F1 squared to F3 dot for the zero momentum. And for the finite momentum P1, I have 0 plus 1 with, I forgot, patch 2 x squared. And for P2, different momentum, then this Bogoliubov transformation is probably different. And if you keep multiplying this for every momentum that is non-zero, and that's the meaning of this tensor product over here.
Understood.
Because we're talking about this multi-body state, in principle can have infinite particles in it, then you have to specify how you diagnose a Hamiltonian for every momentum combinations. And you have to do all of them at once, is the way you can write down the ground state.
Okay, got it.
And it turns out that doing all this stuff with operators is something you can capture just by looking at the classical field equation. And that's why I told you, it turns out the classical field equation is a lot easier than using operators. But you can do it, because after all, they are supposed to be the same thing. And using classical field equation, you also get the advantage of, it's easy to talk about this macroscopic motion of the fluid, either flowing one direction or going in circles. And you can also create a configuration that looks like tornadoes, called vortices. And when you create vortices, you can create Bose-Einstein condensate. You try to rotate the entire system. You find this bunch of tornadoes called vortices. And every vortex would repel with each other. So if you make a bunch of these vortices, it turns out that they line up in a very neat triangular lattice at the end of the day. And that can also be described just by solving the classical field equation. So it turns out that QFT was supposed to be the same thing as quantum mechanics. That's how we started to discuss QFT. But it turns out that QFT is way more powerful, because you can solve the systems you cannot in quantum mechanics. And even just the classical field equation captures very non-trivial physics of highly quantum state of matter, including these real solutions like vortices in the classical field equation. So that's why we use QFT. Okay, I went a little bit over time, but anyway, let me stop here. Any questions? Yes?
Why it is hyperbolic tangent?
Yeah, so I didn't explain, but if you, I'm going to expand the lecture notes. Hopefully I post this again early next week, and you see why tanh is the right coefficient for these higher occupation number modes. And you see that explicitly. Okay? Any other questions? Okay. And if you feel that you're getting a little lost, please don't hesitate to ask me.